Okay, good morning all of you. Let's get started. Any questions from yesterday's class? And I told you to revise your concepts of integration by parts. Okay, and I also asked you to go through the variational concepts that we looked at in yesterday's class. Anyway, I don't know whether you did it or not, but let me go through it once again. So we looked at weighted residual methods, and the next type of method is this variational method. And one of the method is this Rayleigh-Grigg method. Rayleigh-Grigg method is a variational method. For this variational method, you need to have some knowledge in variational calculus. So that is the reason we went through all this process in yesterday's class. We noted what is variation of a function and how this variation operator is going to work under different situations. We noted some of the relations, formulas, and identities. And you have any question related to that, whatever we covered in yesterday's class? Any questions? If there are no questions, then let me go further. And also, I pointed out to you this variation of u can be written in this manner. And the idea of this kind of rearranging this u is, if I want this variation of u to be 0, the only way the variation of u can be 0 is partial derivative of u with respect to the unknown parameter should be independently equal to 0. Okay? And when I say u here, u is a function. U can be anything. It can be potential energy. If it is related to structural systems, it can be potential energy. Any questions here? Then let's go further. And we also noted all these relations. And I mentioned to you in yesterday's class, we'll be using these relations back and forth in the sense in either direction, depending on our requirement. Okay? So you just keep that in mind, and you should you should be very good in doing this. Okay? So you please familiarize yourself with all these things. And before we proceed further with this variational method, I told you to revise the concepts of integration by parts. Okay? Anyway, for completeness, a simple Google search gives you something like this. Integration by parts. What exactly is this integration by parts? And what is the use of it? You please take a note of this relation here. Integration by parts, the first one. This equation. To take a note of that. The same equation can be compactly written as given in the second one. Okay? This I'm taking from some online resources, okay, that is available. So take a note of this equation and this equation. Basically, what this is, integration by parts, first take a note of this equation, okay? And here you are integrating u, which is a function of x, multiplied by another function of x, which is v prime. V prime is nothing but first derivative of v with respect to x. So a product of u times first derivative of v with respect to x, you are trying to integrate. Okay? And that can be written like this. And basically this is very easy to derive. Okay? You please see this second part of this equation, this part, you take this to this side. Okay? You take it to the left hand side. Whatever is appearing on the right hand side, you take it to the left hand side. And this, what is this? It's product of u and v. And that can be written as integral. You please take a note of whatever I'm saying. Integral u times v, or integral in bracket derivative of the product u times v, integral of that. Integral, inside the integral, derivative of product. Product in the sense you need to put a bracket. Product of this u and v, you are taking first derivative of that with respect to x and integrating over x. Okay? And that actually reduces to this, because your integration and differentiation you are doing on the same thing. So it gets cancelled, and finally product of u and v is this one. So that is how you are getting. And if you expand it, you can easily understand what it is. You please try yourself. Okay. So by writing this integration by parts in this manner, what is the advantage of this? What is the advantage of this one? You please see here, u is there. And what is this v prime? First derivative of v with respect to x. I want to shift this derivative. I don't want to take derivative on v, but I want to take derivative on u. I want to shift this derivative. What is the reason? What is the reason I am doing? There can be several reasons which we will discuss. Okay? How to shift this derivative from v to u? For that, this integration by parts is going to be very useful. This relation is going to be useful for that. If you are taking derivative on a function, if you want to shift the derivative to the other function, then you can make use of this relation and then shift the derivative to the other function. You can see here on this side, derivative is appearing only on u, whereas here on this side, derivative is appearing on v. I don't want to take derivative on v, but I want to take derivative on u. So that shifting, it is like a load shifting. It is like a load shifting. Instead of putting a load on one function, you are shifting that load to the other function. So that is the advantage of this integration by parts. And please note that when I say here u as a function of x and v as a v prime as function of x, when I say v prime, even second derivative can be written in this manner. Okay, that we will see in a while. Just take a note of this, and if you have any questions related to this explanation, let's discuss. If you have any question, please raise that at this stage. Integration by parts. Basically, integration by parts is going to be used to shift the derivative from one function to the other function. So, and if you want more, I just did a Google search, okay, and I got this page, and I found this is convenient for my explanation. That's why I pulled this page out. And if you want, you can go through this here. Same thing. Same thing is written in a different way. Here, this is what I'm saying. Okay, this is what I'm saying. Product rule of differentiation. Okay, and using product rule of differentiation, you can write the integration by parts equation. Okay, product rule of differentiation. Now integrate on both sides. So this is going to be integral, and also you are taking derivative. Then it's going to be f times g. There in the previous slide or previous whatever I explained, u and v are used. Here f and g are used. It doesn't matter. So when you integrate the first term, or let me put it in a slideshow. When you integrate the first term, it's going to become f times g, and here it's going to be integral f times derivative of g dx integral f prime multiplied by g dx, and you rearrange that. That is what this one. That is what this equation is. And then you rearrange this, then you get whatever we have seen. And same thing is written here as well. Integration by parts. Any questions here? You should be very clear on this. It may appear very simple, but integration by parts, that entire process is very powerful. It has several applications. Okay? If there are no questions, so let's go through this variational method. What are the various steps? Let's go through them. Given boundary value problem, and this is the boundary value problem that we are looking at. This is the boundary value problem that we are looking at. We solve the same problem using weighted residual methods, and we are trying to attempt the same problem, or we are trying to solve the same problem using variational method. So this is the boundary value problem we are looking at, and these are the boundary conditions. Both the boundary conditions are essential boundary conditions. So with that, so given this is the given differential equation, the first step in variational method or Rayleigh-Ridge method is you be very clear what you are trying to solve for, what you are trying to approximate here. I'm trying to approximate u. So whatever quantity you are trying to approximate, you multiply this equation, the governing differential equation, on either side with variation of that quantity. U is what I'm trying to approximate. So variation of u, I need to multiply on both sides and integrate over the problem domain 0 to 1. So that is what is the first step. That is the first step. So please take a note of it. Please take a note of that first equation. And in the first equation, if you see carefully, this is for one term, and please note that this is nothing but a product here. Whatever is there in the square bracket multiplied with variation of u. Okay? First term involves second derivative of u. And second term is not a function of u. Second term is not a function of u. Okay? And let's focus only on the first term. Second derivative of u is involved. I don't want to take 2 times derivative on u. And what is this first term is going to become? It's going to become integral 0 to 1 minus second derivative of u with respect to x multiplied by variation of u dx. That is the first term. So that first term is written. The first term is taken out and written here. That is the first term. And if you expand it, Or if you, now let's see what is this. Okay, this first term. And here you are taking 2 times derivative on u, and there is no derivative on variation of u. Okay, I want to shift. Instead of taking 2 times derivative on u, I want to shift 1 derivative to variation of u. Is it clear? I want to shift 1 derivative to variation of u. Or if you want, after that, next step, if you want, completely shift the 2 times the second derivative to variation of u, that is also possible. So now I want to shift, instead of taking 2 times derivative on u, I want to shift this derivative, 1 derivative to variation of u. How do I do that? How do I do that? Integration by parts. Integration by parts. So integration by parts is going to result in this. And what is integration by parts? Integral u times v prime dx is equal to uv in the sense, when you have limits on integration, yeah, you need to evaluate this uv at the both the limits. uv evaluated at upper limit minus uv evaluated at lower limit. You just take a note of this. That's why I'm saying you need to keep your notebook and you take a note of whatever we are discussing. So you take a note of this equation. Now instead of u, you have second derivative of u with respect to x square. This is you treat this like a formula. So our u is second derivative of u with respect to x square minus second derivative of u with respect to x square. And what about I want to take back, u is nothing but in this particular case u is nothing but this variation of u, and v prime is nothing but minus d square u over dx square, second derivative of u with respect to x. So now coming back to this one, this formula, u is variation of u, v prime is second derivative of u with respect to x square. Now you apply this formula. And when you have limits of integration specified, then this product needs to be evaluated at upper limit and lower limit. Upper limit minus lower limit. So what is this going to become? What is u in our case? Variation of u multiplied by v. V prime is second derivative of u with respect to x. V is going to be first derivative of u with respect to x, evaluated at both the limits, upper limit minus lower limit. And then second, this term is going to be u prime. U prime is nothing but derivative of variation of u multiplied by v. V is going to be first derivative of u with respect to x. And limits of integration 0 to 1. Any questions here? So that is what is written here. You see here, this equation is coming from integration by parts. This equation is coming from integration by parts. And this, you should be very clear how this is obtained. If you have any questions here, you please at this stage get it clarified. And you have a minus sign here, so it should be upper limit, evaluated upper limit minus lower limit, but because of this negative sign, that gets interchanged. Negative is going to come for the upper limit, positive is going to be for the lower limit. You please see any questions here, integration by parts. Any questions? And if it is clear to you, this is the first term. What about the second term? Second term is not having any derivatives and it's not a function of u. So it's simply minus sine of integral minus sine of pi x multiplied by variation of u dx. So second term is going to be as it is, it's going to be there. Okay. So now this first term you plug in here. First term you plug in here, you are going to get this equation. Take a note of this equation, and if you have any questions, please let me know at this stage. Any questions? I'm going very slow because this is a very important concept and understanding is more important than rushing through the slides. So this equation, have you noted this equation? Last equation. Okay. And now if you had noted this last equation, I want to make use of this concept here. If variation of u, instead of variation of u, I can have something, variation of something inside the bracket. Something inside the bracket, okay? Variation of that is nothing but partial derivative of that something in the bracket with respect to the unknown coefficient a0 multiplied by variation of a0. And similarly, partial derivative of that, whatever is there in the bracket with respect to a2, and this variation of a1 with respect to a1, variation of a1. Similarly, you can you can do like that. Okay. So now this entire equation, I want to bring it into the form. I don't want it to be like this. I want it to be in the form variation of something inside the bracket is equal to 0. Anyway, 0 is there on this side. This entire thing I need to change it in that fashion. Okay. Then only we can apply this variational method. Actually, that is the reason. Not all problems can be brought into that form. Variation of something is equal to 0. Not all problems can be brought into that form. So now let's look at this problem. Can be like you can bring it into that form. Let's see how to do that. And now let's understand what is this term, first term. What is this second term? First term is minus of variation of u multiplied by first derivative of u with respect to x evaluated at x is equal to 1. And second term is variation of u multiplied by first derivative of u with respect to x evaluated at x is equal to 0. At x is equal to 0. What is this x is equal to 1, x is equal to 0? What are those particular locations? What is the significance of that? The significance is at both these locations, essential boundary condition is specified. At both these boundary condition, essential boundary condition is specified. Okay. If only one location essential boundary condition is specified, that alone you put some focus on that. Okay. So here at x is equal to 1, at x is equal to 0, at both the locations essential boundary conditions are specified. And what is variation of u? Variation of u is change in this function u when there are some perturbations in the unknown parameters. When there are perturbations in the unknown parameters, when there are changes in the unknown parameters, whatever change in this function u, that is nothing but variation of u. And while solving problems using weighted residual methods, I told you, or I emphasized to you, even in the last class, I emphasized to you, whatever approximate solution that you get, it has to satisfy essential boundary condition. Okay? Whatever approximate solution you get, it has to satisfy essential boundary condition. Here, x is equal to 0 is a point where essential boundary condition is specified. X is equal to 1 is a point where essential boundary condition is specified. Whatever I told yesterday with respect to weighted residual method, same thing is applicable for any other method. Essential boundary approximate solution has to satisfy essential boundary condition. What is the meaning of that? Essential boundary condition has to satisfy at whatever points you specify, or whatever this essential boundary condition has to satisfy, or the approximate solution has to satisfy essential boundary conditions. What is that means? Approximate solution. We are trying to find approximate solution of U. So approximate solution of U, there cannot be any change in that. There cannot be any change in the this approximate solution at the points where essential boundary conditions are specified. That means, what is that means? That means variation of U at whatever points essential boundary condition is specified, it has to be equal to 0. I don't want any change in the this U. What is variation of U? Variation of U is the change in the function where there are changes in the perturbation of unknown parameters. But at the points where essential boundary conditions are specified, variation of U cannot have a non-zero value. It should be 0. Variation of U should be 0 wherever essential boundary condition is specified. Okay? Here essential boundary condition is U at x is equal to 0 is 0, U at x is equal to 1 is 0. Even if this is a non-zero value, U at x is equal to 0 is some non-zero value. Here also it is a non-zero value. At these 2 points, variation of U should be equal to 0. Wherever you specify essential boundary condition, at those locations, variation of U should be equal to 0. Is it clear? So now you apply that here. Variation of U at x is equal to 1 multiplied by derivative of U with respect to x evaluated at x is equal to 1. This product, since at x is equal to 1 essential boundary condition is specified, variation of U is going to be 0. Since at x is equal to 0 essential boundary condition is specified, variation of U is going to be 0. So these two terms gets cancelled. These two terms vanish based on that explanation. Okay? Then you are left with only this one. Please take a note of that. This last equation, if you are not taken, and also you take a note of this equation without these two terms. So based on the explanation that I gave you, these two terms are going to vanish. Okay? So you are left with only this term, integral 0 to 1, whatever is there in the square bracket, dx is equal to 0. You are left with only that one. So let me go further. And now, this term is there. I told you to take a note of this one. This term alone. These two terms are going to vanish. This term alone equal to 0. You please take a note of it. Okay? And what is this first term? What is this first term? Derivative of variation of U with respect to x multiplied by derivative of U with respect to x. This term. And yesterday you noted one identity or one relation. You please, you can make use of that here. What is that relation? It's nothing but half of this quantity is nothing but half of variation of derivative of u with respect to x square whole square. It's going to be variation of this is what I'm saying. This is what I'm saying. The first term is nothing but this one, and the second term is looking like fx times variation of x. Fx times variation of x, that can be written as variation of fx times u. So the first term can be written like this, second term can be written like this. And whatever is there in the square bracket, these two terms are there in the square bracket. So first term is written like this, second term can be written like this. And now this is looking like half is a constant. Okay, it doesn't matter. You can pull you can take this half inside the variation symbol. You can take the constant inside the variation symbol. So it's going to be looking like variation of u minus variation of v. It's going to be variation of u minus v. Is this clear? So if this is clear, then you can rewrite the previous equation in this manner. And here actually these two quantities are going to be vanishing, but there's still that step is not applied. So that's why they are written here. Okay, these two terms in addition. You can see here this term, whatever is there here, that is recasted or rewritten such a way that something inside the bracket or variation of something inside the bracket. Okay, so that is what is written here. Please take a note of this last equation. Any questions? Let me see, any comments are there here? They're keeping silent means I'm hoping there are you're following or everything is clear to you. Okay,
sir. Sir, one question. Sir, why sin pi x u of x subtracted?
What sin pi x? Here, this one.
Yes, sir. Why it is subtracted in the before slide?
What here? It is a
yes,
minus sign is there, no? Here,
yes,
minus sign is there. Here, it is coming from the equation.
Okay.
It's coming from the equation. That's why I'm saying you please take a note of it. Okay, you take whatever my suggestions. You take it in a positive sense, because we are working or it's not a regular classroom. Okay, unless you take a note of it, it's not going to be something like you listen Ramayana, Mahabharata or something like that. It's not like that. You just take a note of this. You take a note of this equation, then it actually that negative sign follows from there. Okay?
Yes,
Here.
sir.
So now I got this into the desired form. Okay, I got almost into the desired form except the first two terms. Somehow I can, whether I have to see whether I can bring the first two terms inside this or not. But in this case, essential boundary condition is specified at x is equal to 0, x is equal to 1. Wherever essential boundary condition is specified, it need not be 0 essential boundary condition. Okay, it can be any non-zero value. Wherever essential boundary condition is specified, at that location variation of u is going to be 0. Based on that reasoning, these two terms are going to get vanished and you will be left with only this one. You will be left with only with this one. And please note that whatever is there in this square bracket, everything is function of u. Everything is function of u. And that function of u is written in this manner, because integral is also there. It is written as iu. This entire thing is written, whatever is there inside this curly bracket. Inside this curly bracket, whatever is there, that is denoted with I. It's function of u, so iu. So iu is defined like this. Whatever is there, this term is iu. So now you see whatever we noted. What is variational method? In variational method, the given boundary value problem is expressed in an equivalent variational functional. So this is what that means. So now I have something, variation of some function of u is equal to 0. When this is going to happen? You now bring in whatever I repeatedly mentioned here. Variation of u is equal to 0 is possible only when partial derivative of u with respect to the unknown parameters. Variation of u is going to be 0 only when partial derivative of u with respect to the unknown parameters is with respect to each of the unknown parameters is independently equal to 0. Okay, so you bring in that here. You have variation of the function of u is equal to 0. So this is possible only if partial derivative of I with respect to the unknown parameter should be equal to 0. Okay, and now please note that we started from here, and we went through all this process, and finally we got in here. We are now here. But from the first step till now, we never thought about what should be u, what should be the trial solution for you. Okay, what should be at this stage we need to start, or we need to assume some trial solution of u. So let u be a quadratic trial solution, similar to what we did for weighted residual method. Let u be quadratic trial solution. So if u is quadratic trial solution, what is second derivative of u with respect to x? You already have all that with you when you did with weighted residual methods. If you want, I will go to that slide once again. Okay. So what I am saying is, till this point we never assumed what should be the trial solution. So now this process is required. Till this point, any problem, you need to follow the same procedure and try to bring it into this form. Variation of some function inside the bracket is equal to 0. You need to bring the given boundary value problem into that form, and that is required. From there we are going to start with a trial solution. Okay, and then the problem with this kind of variational method is not all problems you will be able to bring into this form. Not all problems you will be able to bring into this form, but in you can solve this, those kind of problems using weighted residual methods. But don't worry, all civil engineering related, or this mechanical engineering or mechanics related, whatever the differential equations or whatever boundary value problems that you encounter, you will be able to bring it into this form. You cannot give that excuse and say I cannot solve the problem. All mechanics based problems you should be able to bring it into this form. Whatever statement I made, that not all problems cannot be brought into this form. That is a general one. Okay. So now with that, let me show you starting with quadratic here. Starting with quadratic trial solution, what we did in weighted residual method. Starting with quadratic trial solution, make sure that this trial solution becomes admissible by satisfying essential boundary conditions. All that is required, even for variational method. All that is required for variational method. Okay? And then you make this trial solution admissible, and whatever required derivatives you take, first derivative, second derivative, you please take a note of it for completeness. Now we are going to substitute this in that variation of some function inside the bracket is equal to 0. That function, in that function we are going to substitute this. Okay. So please take a note of it. And now I want to ask you a question. Now you have the admissible trial solution. Admissible trial solution U is there. Now you apply variation operator on this U. Now you apply variation operator on this U. What it's going to be? When you apply variation operator on this U, it's going to be delta A2 multiplied by this function. This is not a function of this. It is like fx times a constant, fx times a constant, or unknown parameter, fx times unknown parameter. So variation of U is going to be variation of A2 times this. And why I am telling that? Now you can check here itself. What is variation of U evaluated at x is equal to 0? Wherever essential boundary condition is specified, what is variation of U? What is variation of U at x is equal to 0? Variation of U at x is equal to 1? It's going to be 0. If you did this, whatever trial solution you started out with, when you make it admissible, automatically variation of U, wherever you specify essential boundary condition, it's going to be 0. Automatically it's going to happen. Any questions here? Okay. So whatever explanation I told you, and based on that explanation, whatever I did, that is cancelling these two terms. If you did not like that, explanation, and you don't agree with that, then you can once you get the admissible solution, once you get admissible trial solution, you can find what is variation of U at the point where essential boundary condition is specified, and then check whether that is equal to 0 or not. That way also you can do. Okay. Anyway, think about it. Maybe you think about this problem and also look at the assignment problems. Then you will get more questions. Maybe we'll discuss in tomorrow's class. Okay. So now this second derivative of U with respect to x, or sorry, first derivative of U with respect to x. This is first derivative of U with respect to x. Just now we noted what it is. So you substitute that here. Okay. And this is anyway its function of x. And here you substitute admissible solution. A2 multiplied by minus x plus x square. That you substitute here. Then finally this U, sorry, this I is going to be a function of unknown parameters when you do all that. So U is this. Whatever explanation I gave you, that is all given here. U is this. Variation of U is this, and you can cross check wherever essential boundary condition is specified, if you did this, properly, if you got this admissible trial solution properly, then these two conditions automatically get satisfied. If there is a mistake, that you made in getting this admissible trial solution, then these conditions may not be satisfied. And now I as a function of u, when you substitute all this, it's going to be a function of I becomes function of unknown parameters. How many unknown parameters are there in the admissible trial solution? How many unknown parameters? Only one parameter is left out, A2. So you are going to get I as a function of so many parameters as so many unknown parameters that are appearing in the admissible trial solution. Since admissible trial solution, you have A2, I is going to be a function of 8. I is going to be a function of 8. So variation of I variation of I is equal to 0. That is what this equation is. So variation of I is equal to 0 only if partial derivative of I with respect to the unknown parameter is equal to 0. What is unknown parameter? A2. So you take partial derivative of I with respect to A2 and equate it to 0, and you are going to get one equation, because you need to determine only one unknown parameter. Suppose in the admissible solution, you end up in getting two unknown parameters. When you start with a cubic trial solution, or for some other problem where you have essential boundary condition, natural boundary condition, yeah, it may turn out that this admissible trial solution consists of more than one unknown parameter. Then you are going to get so many equations here. So you need to take partial derivative of I with respect to A2 here. It's taken only with respect to A2 here, but in that particular case, you may need to take with respect to more number of parameters. So you are going to get so many equations as so many unknown parameters. So you need to solve that linear system of equations. So here only one equation is there because we have only one unknown parameters. We can easily solve this and find what is A2. Please take a note of it. Please take a note of this and then find what is A2. Please take a note of this. And what is A2? A2 is nothing but minus 12 divided by pi square. And the approximate solution is going to be this. And what is the approximate solution that you got from Galerkin method? What is the approximate solution you got from the Galerkin method? There is no response. I think, I don't know whether you are following or not.
It was same.
It was same. That is what you need to realize now. IIT Madras, from entrance you have two paths to reach the hostel. So whether you take, it doesn't matter whichever path you take, finally you are going to reach your destination. So Galerkin method and variational method are two approaches to solve a boundary value problem. If you had done properly, without mistakes, you see totally different path we have taken. But we got identical solution, exactly same solution. So similarly, if a boundary value problem you are able to solve using variational method and Galerkin method, you are going to get same solution. Only thing is the approach is different. Approach is going to be different, but you need to get, you have to at this stage you need to force yourself to keep in mind that both solutions should be same. If a particular boundary value problem or if a particular problem cannot be cannot be brought into this kind of form, which is requirement for variational method. If a particular problem cannot be brought into this form, that is a different issue. Okay, but if you are able to get into this form by using all these variational properties and other things, you should get the same solution as what you got from the Galerkin method. Okay, so error is going to be, or that plot is not reproduced here. That plot is its same solution. So plot is going to look like this. Okay, so I'm going to stop here. And the next method is modified Galerkin method. What is this modification? In today's class, if you had carefully, I don't know if you have followed, first of all, please note that you should be serious in this course. And there is nothing like some students are asking, they want to do auditing of this course and other things. If you want, you can do auditing, but you are not going to learn anything unless you attempt the problems. In finite element method, you need to solve problems on your own. Okay, then only you will understand this properly, this method. And also, not solving the problem on pen and using pen and paper, you should actually have some coding, you should be able to do some coding. Then only real strength of this method is going to come out. Okay, and here you see, for understanding purpose, we are taking some problems where we have one unknown, one equation, or two unknown, two equations. But in reality, you are going to have more number of unknowns, more number of equations. So you need to write some code for that, for solving that. Anyway, the point I want you, or whether you have observed it or not in today's class, this is what integration by parts. Integration by parts, whatever you learned in today's class, one more important point you should have noticed. Here, basically, second derivative of u is there. By using integration by parts, in today's class, what we did is we reduced the order of integration on u. Instead of taking 2 times derivative on u, we transferred one derivative to variation of u. The same logic can be applied anywhere. So that is what that modified Galerkin method. If you see Galerkin method, in Galerkin method, here in the error function we took the derivative 2 times. Okay, instead of this, can we shift the derivative to this weight function? Can we shift the one derivative to this weight function? So that is what is modified Galerkin method. We'll discuss that in tomorrow's class. Okay. Anyway, I think this time is running out. I'll stop here. So in tomorrow's class, we'll look at this modified Galerkin method. This is also based on integration by parts. Okay, any other questions? Just wait a minute. Let me take attendance. Okay, thank you.